Okay. Hi everyone, my name is Liu Huiqi. Now I will make a presentation about the epsilon delta definition of the limit of a function. I will start with a brief introduction about the idea of limit. The concept of a limit is very important in calculus and mathematical analysis. Intuitively, a limit describes how a function behaves when the input value gets closer to a certain point. Even if the function is not defined exactly at that point, we can still study what value the function is approaching. To understand this more clearly, let me first explain the intuitive idea of a limit. Suppose we have a function fx and a point x0. If the value of fx become closer and closer to some number L as x approach x0, then we say that the limit of fx is L. This idea helps us understand the local behavior of a function. However, this intuitive idea is not enough for mathematical proof. In mathematics, intuition alone is not sufficient. Different people may interpret getting closer in different way. So in order to write a correct and rigorous proof, we need a precise definition of a limit. So to make the idea precise, we use the epsilon delta definition. According to the epsilon delta definition, we say that the limit of fx as x approach x0 is L, if and only if, for every positive number epsilon, there exists a positive number delta, such that whenever x is close enough to x0, the value of fx is close enough to L. And then I will explain what this definition actually means in simple words. So let's use the diagram to understand the epsilon delta definition of a limit. On the horizontal axis, we have the input x, and on the vertical axis, we have the output fx. The horizontal dashed line represents the epsilon range around the limit value L. This shows that how close the output fx needs to be L. The vertical dashed line represents the delta range around x0. This shows how close the input x needs to be to x0. In simple terms, epsilon controls how close fx is to L, while delta controls how close x is to x0. The key idea is that for any epsilon greater than 0, we can find a corresponding delta greater than 0 such that whenever 0 is less than the absolute value of x minus x0 and less than delta, the output satisfies that the absolute value of fx minus L is less than epsilon. The diagram helps us visualize how controlling the input using delta ensures that the output stay within the desired epsilon range. With this definition in mind, we can now prove a simple theorem. So the theorem states the limit of x squared as x approach 1 is equal to 1. Let me go through the proof step by step. So let epsilon be greater than 0, and then we will rewrite the expression absolute x squared minus 1 as absolute x minus 1 times absolute x plus 1. This step is important because it separates the expression into a part we can control and a part we need to bound. And then we need to choose a suitable delta. We choose the delta to be the minimum of 1 and epsilon over 3. We choose delta less than or equal to 1 because we want to restrict how far x can move away from 1. This restriction helps us control the value of x plus 1. And then we look at how this choice helps us control the term x plus 1. Hey, since absolute x minus 1 is less than 1, so x must be lie between 0 and 2. Therefore, x plus 1 lie between 1 and 3. This means that the absolute value of x plus 1 is less than 3. With these bounds, we can now complete the proof. We put everything together. we have absolute x squared minus 1 equal to absolute x minus 1 times absolute x plus 1. Since absolute x plus 1 is less than 3 and absolute x minus 1 is less than epsilon over 3, so the whole expression is less than epsilon. Oh, wait. And then we prove that the limit of x squared approach 1 is equal to 1. And then the next, I will give an example to show how limit work in another situation. We consider the limit of 1 over x as x approach infinity. Intuitively, as x becomes larger and larger, the value of 1 over x becomes smaller and smaller. So one way to explain this limit is using sequence. If a sequence xn goes to infinity, we use the same mind just now, then the value of xn become very, very large. As a result, the value of 1 over xn become very small. So given an epsilon greater than 0, we can choose n large enough such that 1 over xn is smaller than epsilon. This shows that the limit of 1 over x as x approach infinity is equal to 0. That's all for the example proof, and then I will briefly explain why this definition is important. The epsilon delta definition is important because it provides a rigorous foundation for calculus. It is used to define continuity, derivative, integrals, and so on. Without this definition, calculus would not be mathematically precise. That brings me to the end of my presentation. Thank you for your watching and listening. That's all for me.